Okay, thank you. So the topic today I will talk about the K-radial sequence. So it was a work I have done about 6 years ago, and when I was a postdoc here with Xiande. So at that time we just got a very weak result, and then worked on other problems. So about 2 years ago, I found some papers written by other people, and I found their methods are very interesting. So I work on this problem again and try to find some progress. So yeah, I started 2 years ago, but the progress is very slow. So I think I'm not smart enough, and I tried very hard to make connections of this problem, make connections with this problem to some other workers of like Brody and Stevens and Inwanis. So I want to take this opportunity to seek discussions on it. Okay, so the problem is the definition is very simple. So everything is very simple, I think. So sigma is an n-element alphabet, and we have an n-array K-radial sequence. So the elements are from sigma, and it's a finite sequence. And the property is that any two distinct elements of sigma should appear in this sequence somewhere at distance at most k. Yeah, this is like the strength is k. Yeah, so the distance here we mean in the distance of two distinct elements in this sequence, we mean just the difference of the corresponding positions of these elements in the sequence. So let's look at a very simple example. So sigma here is the cyclic group AH, and k equals 2. So we should check the pairs in this sequence, the pairs of two distinct elements in this sequence of distance 1 or 2. So for example, the 3, 6 here have distance 1, 3, 2 here have distance 2, and etc. And you can check this is, so it is 8 array because we have 8 elements and 2 radial sequence of length 17. So you can check some of them. So for example, 0, 1, we have distance 1, 0, 2, distance 2, 0, 3, distance 2, 0, 4, distance 4, and 0, 5, 0, 6, 0, 7 here. So any pair of distinct elements should appear at distance 1 or 2 in this sequence. So this sequence, is a line, so it's a linear sequence. So some pair could appear more than once in this sequence. So 0, 7 here once, and 0, 7 here once. So if you don't care about the length of this sequence, so it is easy. It always exists. You can start from any partial sequence and check the pairs whether they appear or not. If it doesn't appear, then just add to the end of this sequence. So this is just the problem, and it was introduced by these two guys. I don't know how to pronounce their names, so I just call them J and L in 2004. When they consider some problems about the computations on MR slices. So as just I mentioned, if you don't care about the length, they always exist. So we are interested in the shortest length. So we denote it by FKN. So the example gave F2H is less than or equal to 17, and in fact, by computer search, we can verify it is equal to 17. And when k equals 1, it is like trivial. You can, by the definition, so you need every pair of the elements, should appear adjacent in the sequence. So related to the Euler cycle of the complete graph. So if n is odd, there exists such an Euler cycle, and then just cut it to a line, then add the first element to the end. Then you got it. And for even it's similar. So it has been determined by Gaussian a long time ago when they consider another problem. And so the main question here is just to estimate FKN or determine it. And we don't have many exact values of this FKN. We will see later. And the lower bound is given by these two guys. And which we look at this lower bound, there are two terms here. The major term is about n squared of 2k. And here is the minor term. Minor term, it depends on n. And but up-bounded by k, you can check up-bounded by k. So if k is a constant, so this RKN is bounded by a constant. It's bounded by a constant. And here is asymptotic results in the literature. We have logic here. So F2n is about n squared over 4. It's just equal to the major term. The major term is correct. And later, by Blackman and Mikey, so they prove this. This is also true for some k and some conditions. And then by using a probabilistic method, they show this is true for every fixed k. For every fixed k, and you can see from this formula, if you have a minor term, the minor term is still small o of n squared, So it can be proved by this guy. So he proved it to be n to big O of n to the 1 plus epsilon for every positive epsilon. Epsilon, you should write epsilon here. So they conjecture that this epsilon can be removed. This is work by Zhang in 2016. So yeah, I read their papers and I just try to work on this problem again. So in their paper, they have given, I think there are 3 conjectures, but I'm interested in these 2 conjectures. The first one is a weak conjecture, just FKN for every fixed k, FKN equals the n squared of 2k plus big O of n. So the mandatory is big O of n. And the second one is a stronger one. They conjecture the lower bound can be achieved for most of n. And so far there is only one exception, up to 9. This is one more than the lower bound, just one more than the lower bound. And they gave some exact values for k equals 2, but no complete result. And when k is a prime power, it comes from the different sets. And actually, they gave a lower bound of this F2n. So the minor term is also a constant, but bigger than this one. So it's a very good result, but just for k equals 2. And there. So here comes to the construction. So originally we define a linear sequence, but linear sequence is not good to analyze. So we can construct a cyclic sequence first. It's like a cycle then cartridge. So the cycle also satisfies some k-radius sequence, k-radius property. So then we cartridge, then becomes a line, and just add the first k terms to the end of the sequence, and then we got a linear sequence. So we have, so we denote the GKN is the short length of this cycle, and we have relations of the GKN and FKN. So in their paper, they reduce the whole problem to this one. So you can find, so from here you can see every symbol should appear at least n minus 1 over 2k times. It's a very easy argument, you can get this. And so when n is equals 1 modulo 2k, so should be equal to, if you can prove it equal to this one, then you can prove this FKN equal to the lower bound, to the lower bound. And so we change the problem to a to a cycle, and to construct this cycle, so we need to they define another sequence. It's called K-additive sequence. So it's like a generator. It's like a generator. It's a much shorter generator. So here you need to construct the cycle of length n times n minus 1 over 2k. So for additive sequence, so you only need to construct a cycle of n minus 1 over 2k. Okay. So here n equals 2ks plus 1. So here s is just n minus 1 over 2k. So the k-additive sequence have length s, and it's also a cycle, and satisfy this property. So we collect the sums of consecutive terms up to k consecutive terms. So you can say ai plus 1, and ai plus 1 plus ai plus k minus 1. So up to the sums of up to k consecutive terms. So for each I, we have k sums here. So in total we have ks values here. Then take the positive, negative. So we have 2ks values here. So we need it to be equal to zn minus 0. So each non-zero element appear in this set exactly once. So this is called the k-active sequence. And we denote the sigma is just the sum of all the terms in the cycle. So here is an example. We show an example and show how to use this k-additive sequence to construct a radial sequence. So k equals 2 here, s equals 3, so n is 13. So we have a cycle of length 3. So 1, 2, 7. It is 2 additive sequence of length 3, because if you check the sums of one term is just 1, 2, 7. The sum of two consecutive terms is 1 plus 2 equals 3, and 9, and 7 plus 1 equals 8. Then take the positive, negative. It's just z13 minus 0. So it's 2 additive sequence. And sigma here, the sum of these 3 terms is 10, and the GCT is 1 here. It's 1 here. So from this additive sequence, we can construct a radial sequence as this way. We start from the symbol 0, then add 1 to 0, 2 to 1. So add 1 to So add 1 to 0, we get 1. Then add 2 to 1, we get 3. And add 7 to 3, get 10. Then repeatedly add 1 to 10, get 11, and again. Okay. Can you hear me?
Yeah.
Okay.
Without the microphone.
I will try myself to speak louder. So. So by adding these elements repeatedly, we get a long sequence. And finally, this sequence will come to the beginning of this sequence. So you can check you add 1, 2, 3, here you get 4, and add 2 to 4 you get 6, and add 7 to 6 you get 0 again, and then add 1. So come to the beginning again. So it forms a big cycle, and you can check any two elements of this Z13 appear in this cycle. This is 1 or 2 exactly once. So it's likely that because of the GCD is 1, so we only form just one cycle. So this is exactly what we want. So you can conjugate to form more lines, then you can determine the FKN. So if the GCD is bigger than 1, so we suppose it is D, then you can get D cycles by this method. So you can start from 0, then add these elements repeatedly to get x0, then you start from 1 to get x1 is also a cycle. Start from 2, then start from D minus 1, you get in total D cycles. So for each cycle, so in these D cycles, you can check any pair of the elements will appear in some of the D cycles within distance k exactly once. Then you can just count these cycles and then combine them together to get a long cycle, which is k radius sequence. So that's the main idea of the construction. And they deduce that if you have a k additive sequence of length s and D is the GCD of sigma and n, so if D equals 1, then the stronger conjecture can be is true if D equals 1. So if D is bigger than 1, then it implies the first conjecture, the weak conjecture. There is a minor term which is big O n. Okay, so my work is about is focusing on the construction of additive sequences. And okay, this is the null results for D equals 1. So for k equals 2, so this guy bunch in 1983 they constructed the sequence by using another name. So it happened to be a two additive sequence with D equals 1. And they conjugate or they construct other sequences. And for me, I also construct some sequences, but it's still not complete. And the k is a prime power. When k is a prime power, as I just mentioned, can use the different set to get such a sequence. And the k equals 3 and 4, we can only get some examples by computer search. This g equals 1. Okay, so here I mentioned some related problems. So these guys, Eldred, Ale, Mikey, and Wallace, they defined Euler sequences in this paper when they consider some problem related to experimental designs. And Devon and Stevens, in their book, Ordering Block Designs, so they defined the cyclic different sequence. So both of these sequences, they consider, it's also considered a cycle, and they consider the sum of they consider the terms and the sum of two consecutive terms, and they need them satisfy some constraints, and from this they can get the structures they want. So, but they only consider the sums of two consecutive terms. That is just k equals 1 in our case. So, but we want more. But the constraints are different. And for the universe cycles, it was introduced by Fantrin and Grimm a long time ago, and there is a big progress by Herbert in this paper. They also use a similar idea. They form a generator, then develop it to be a universe cycle, but their case is much more complicated because I just mentioned the the definition of universal cycle of k sets of an n set. So we have an n set, and we want to construct a cycle and of length n choose k. So we want each k subset of this n set should appear in this cycle. Should appear in the cycle as a consecutive k terms. Okay, this is a universal cycle. So we use all of them we use a similar idea but different constraints. Okay, so yeah, I tried to construct the key edge sequences, and here we formulate this result, and this result is by application of the Weir's theorem on the grouped sums. And Brody has done a lot of excellent works on how to apply this Weir's theorem to construct designs that we need. And here is the idea is similar. For example, we want a 3 additive sequence, and we just fix the form. We want the sequence look like this, and it's 1x, y, h, hx, hy, and etc. And so here g is the primitive element of the m, and h is g to the power 18. Then we want the sequence of this form, and so it should satisfy some constraints by the definition of three additive sequences. So by applying Weir's theorem, we can find such x, y exist. So this is the main idea. For general k, it's much more complicated, but finally we are able to formulate these two families. So by applying the Dirichlet prime theorem, we can say that there are infinitely many primes in these congruent classes. So there are infinitely many values of n that the first conjecture holds. That is a weak conjecture. And I want to introduce another one that is from the different set. From the different set, we construct a k-radius sequence. So from the different set, we can list them in an increasing order. Then we construct a sequence like this: d1 minus d0, d2 minus d1, and the last one is d0 minus dk plus v. So you can check the sums of up to k consecutive terms, because this is a different set. So this collection is just 1 to v minus 1. So if you take the positive negative, then it's just the non-zero, all the non-zero elements of say 2v minus 1. So it's a k-additive sequence, and luckily the GCD here is just 1. So you can form only one cycle. So because we don't have many different sets of index 1, so we can turn to the difference family. So for example, we have 2 blocks here. Then we can use the similar methods. We can form 2 cycles. Then you can draw the 2 cycles to a long sequence that is the k-radius sequence. So this is the main idea. But difference families with index 1 is also very rare. So we again turn to the cyclic packing. So packing is similar to the difference family, but each non-zero element of this will appear at most once. This is cyclic packing, and so from this we can formulate this theorem. That is, if you have such a cyclic packing, that is for the orders in a congruent class, and I forgot to define the difference leaf. So the difference leaf is just the non-zero elements that hasn't appeared in the cyclic packing. So if the size of the difference leaf is no more than a constant, then we can we can conclude that the weak conjecture is true. So the whole problem can be induced to this theorem. So I checked the literature. We can find this for K3 and 4 the conjecture is true. But for K is bigger than 5. We don't know because there are very rare results about cyclic packing. And here I want to introduce this sequence, which is because the KH sequence we consider about the sums, but for design theory we usually consider about the difference. So I define this sequence, cyclic sequence D0 to ds minus 1, and you can. I check, I need the March set. It's also a list of differences, but we only care about the differences of 2 elements in this sequence with distance at most k. We check the differences. So if this is just Zn minus 0, we call it the generalized k difference sequence. So this k difference sequence is equivalent to the kh sequence with the GCT equals n. And so they are equivalent. So we can get this result by the KH sequence. So here I said generalized because I have I define another K different sequence which corresponds to a KH sequence with the GCT equals 1. But that one is a little bit complex. So and I don't have results on that one, so I don't talk about it. But I think this one is interesting. It's look like an extension of different sets, but it's ordering, and we only consider the differences of elements within distance k. Okay, so I think this is all. Thank you.
Xiande, I'm sorry for your troubled talk. Quick questions? Jonathan?
Is there a relationship between these sequences and Skolem sequences?
Scholar?
Skolem. S-K-S-A-O-L-E-M.
Skolem is I'm not sure if it's about k equals 2, because here we want k is more than 2. I'm not sure.
I don't know. I think it sounds similar, and maybe there's some techniques from one could be applied to the other. Just a comment, not a question.
Okay, thank you. I will check it. Thank you.
Yes, I also wanted to ask, maybe it is a naive question, if there is some relationship with perfect cycle systems. Perfect cycle systems.
Perfect cycle systems.
Perfect cycle systems. But maybe it is a naive question.
I'm not clear about this.
Okay, we will speak at lunchtime. No other questions? So, thanks again, Xiande.